In the previous video, we derived the Fourier transform and its inverse by letting the period of a periodic extension go to infinity. Now we have two powerful formulas. X of omega equals the integral of x of t times e to the minus j omega t, and x of t equals 1 over 2 pi times the integral of x of omega times e to the plus j omega t. But does this integral always converge? And what does the Fourier transform look like for specific signals? In this video, we'll first establish the convergence condition, then compute our first Fourier transform examples, impulse functions, impulse pairs, and the rectangular pulse. For the Fourier transform integral to have a finite value, we need the absolute value of the integral from negative infinity to infinity of x of t, e to the minus j omega t dt must be less than infinity. Using the triangle inequality, this is less than or equal to the integral of the absolute value of x of t times the absolute value of e to the minus j omega t dt. Now here's a key fact. The magnitude of a complex exponential is always 1. Since e to the j theta equals cosine theta plus j sine theta, its magnitude is the square root of cosine squared theta plus sine squared theta, which equals 1. Therefore, the absolute value of e to the minus j omega t equals 1, and our condition simplifies to the integral from negative infinity to infinity of the absolute value of x of t dt must be finite. This is called absolute integrability. If a signal is absolutely integrable, its Fourier transform exists. If not, the transform may not converge in the ordinary sense. Note, however, that generalized Fourier transforms using delta functions can extend this to signals like cosines and step functions. Let's compute our first examples. Example 1. Find the Fourier transform of a single impulse. X of t equals a times delta of t minus t0. Applying the ft integral and using the shifting property of the delta function, x of omega equals the integral of a delta of t minus t0 times e to the minus j omega t dt, which equals a times e to the minus j omega t0. So a shifted impulse maps to a complex exponential in the frequency domain. Example 2. Find x of omega for x of t equals delta of t plus t0 plus delta of t minus t0. This is a symmetric pair of impulses. Using linearity, x of omega equals e to the plus j omega t0 plus e to the minus j omega t0. By Euler's formula, this equals 2 cosine of omega t0. Example 3. X of t equals delta of t minus t0 minus delta of t plus t0. This is an antisymmetric pair. The transform gives x of omega equals e to the minus j omega t0 minus e to the plus j omega t0, which equals minus 2j sine of omega t0. Notice, symmetric impulse pairs give a real cosine spectrum, while antisymmetric pairs give a purely imaginary sine spectrum. Now let's compute one of the most important Fourier transform pairs in signal processing. Let x of t be a rectangular pulse of amplitude 1, extending from minus capital T to plus capital T. Applying the ft definition, x of omega equals the integral from minus t to t of 1 times e to the minus j omega t dt. Integrating the exponential, this equals e to the minus j omega t divided by minus j omega evaluated from minus t to t. Substituting the limits, 1 over minus j omega times the quantity e to the minus j omega t minus e to the plus j omega t. Rearranging, 1 over j omega times the quantity e to the j omega t minus e to the minus j omega t. The numerator is exactly 2j sine of omega t by Euler's formula. So x of omega equals 2j sine of omega t divided by j omega, which simplifies to 2 sine of omega t divided by omega. This can also be written as 2t times sinc of omega t over pi, where sinc of x equals sine of pi x over pi x. This rectangular pulse to sinc function relationship is fundamental and appears throughout signal processing, communications, and sampling theory. Let's summarize what we've learned. First, the convergence condition. A signal must be absolutely integrable for its Fourier transform to exist in the classical sense. Second, we computed three key ft pairs. A shifted impulse A delta of t minus t0 transforms to A e to the minus j omega t0. A symmetric impulse pair transforms to 2 cosine of omega t0, and a rectangular pulse from minus t to t transforms to 2 over omega times sine of omega t. These are building blocks that we'll use extensively. In the next video, we'll explore the relationship between Fourier series and the Fourier transform and build a comprehensive table of transform pairs.